Okay, so section 5.7 here, we're going to look at what's called a change of base. And basically that's simply rewriting a logarithm in terms of another base. For example, if I give you the logarithm log base 2 of 7, my base is 2. We're going to be able to see that we can rewrite that expression log base 2 of 7 as log base 8 of 7 over log base 8 of 2, or for that matter log of whatever number we choose to be a base, log of 3, log base 3 of 7 over log base 3 of 2. Why might we want to do that? Well, if you're asked to evaluate this expression, 2 to some power equals 7, we don't have a log base 2 button on our calculator. We don't have a log base 8 button on our calculator either. We do, though, have a natural log button on our calculator, and so we could rewrite this as log base 2 of 7 is natural log of 7 over natural log of 2, and then we could get a decimal approximation on our calculator for that expression. So in summary, why might we want to change the base for a logarithm? Because a calculator has a base of e, it has a natural log button, and it has a base of 10 log button. Those keys are there and we can get decimal approximations. So as an example, let's consider, suppose we want to find to the nearest thousandth what log base 7 of 91 is. Well, I have some sort of idea about where that's going to be. 7 to some power equals 91. 7 squared is going to be 49, and 7 cubed is going to be a lot bigger than 91. So somewhere between 2 and 3, probably closer to 2. So how would we do this? Key is to let that log expression be equal to some value, let's say y. Rewrite our log expression as an exponent. So then I would have 7 to the y equals 91. Base to exponent equals output. Note this whole thing, this whole logarithm expression, y is an exponent. And then I've got to look at this and say, hey, 7 to the y, that's always going to be a positive number. 91 clearly is a positive number. If I have two positive numbers, would the natural logs of two positive numbers be the same thing? Of course, because if these two numbers are equal, if you look at e to some power equals 7 to the y, and e to some power equals 91, well, since 7 to the y equals 91, those exponents would have to be equal. So natural log of 7 to the y equals natural log of 91. I've taken, arguably, if you will, the natural log of two positive numbers, no problem, two positive numbers that are equal. So then I go back and I've got my law of logarithms, my exponential law of logarithms, which allows me to bring this y out front and write it as y natural log 7 equals natural log 91. And dividing both sides by natural log 7, I get y equals natural log 91 over 7. And note that y was the expression that we were trying to find an approximation for, log base 7 of 91, is indeed y. So I think I just go to my calculator and type in natural log of 91 divided by natural log of 7, and it will spit out a decimal approximation. Now I chose here to take, on the left side, I took the natural log of two positive numbers. I could have taken log base 10, the logs of those two positive numbers, and again use my exponential law of logarithms to bring the y out front. Y log base 10 of 7 equals log base 10 of 91. Solve for y. I get y as log base 10 of 91 over log base 10 of 7. And again, my calculator has a log base 10 button on it, the log button. So from the previous slide, you can see that we can generalize this. If I want to change my base for log base a of b, how do we do it? Well, we set our log expression equal to some other value, say y. I rewrite base to exponent equals output. I then have two positive numbers that are equal. I take their logs, take the log of each side, and say your base, you're going to take base t in general. So log base t of b is going to equal log base t of a to the y. The y then is going to slip down front by my law of logarithms exponential rule. And so I've got y times log base t of a equals log base t of b. Want to solve for y, because that's what log base a of b is. Solve for y, I divide each side by log base t of a, and I get y equals log base t of b over log base t of a. And again, in general, we want to either use, for t, in general we want to use e as a base, and using natural logs, or 10 as a base using our common logs. So in general, log of a log base A of B equals natural log B over natural log B over log A. So one specific example, suppose I want to solve for x. 3 to the x equals 14.3. To solve for x, I'm done in one step. Definition of a logarithm. Base, exponent, output, base, exponent, output, log base 3 of 14.3 equals x. I'm done. Now my change of base formula, if you noted, if you're trying to find a pattern for it, is I can go top to bottom, and it's the natural log of 14.3 over the natural log of 3, or the log of 14.3 over the log of 3, and that is about 2.421 when I plug this in my calculator. Now, I can memorize that change of base formula, and that's great. I think it's a pretty easy one to memorize. Again, we're going top to bottom, log of a number over log of a number. Pick your base. Either common log or natural log is the most appropriate to use because that's what you got on your calculator. However, I could just go back and say, hey, right from the beginning, I want to solve for x here and get a decimal approximation, let's say. I have two positive numbers. This exponential function, regardless of what x is, that exponential function is always positive. 14.3 is positive. The natural log of two positive numbers that are equal, then those natural logs will be equal. So natural log of 3 to the x equals natural log of 14.3. Law of logarithm allows me to bring my x down front. So x times natural log 3 equals natural log of 14.3. Solve for x, I'm going to divide each side by natural log 3, and I get natural log of 14.3 over natural log 3 simply by, again, using my process to solve and isolate change of base. So that's section 5.7.